So I'm Madars Virza, and I'm going to tell you about verifying computations succinctly and in zero knowledge. So let me first get straight to the punchline, and it is this: that correct executions of arbitrary C programs can be verified in a few milliseconds and using a non-interactive proof that's just 322 bytes long. And this talk is going to be about a primitive with a funny name called SNARKs, which stands for Succinct, Non-Interactive Arguments of Knowledge. More precisely, we are going to talk about the pre-processing zero-knowledge kind of SNARKs, but for simplicity through this talk, I'll call them just SNARKs. And SNARKs work like this. There is a prover and a verifier and a common reference string set up in the sky. And the common reference string has two parts: one long for the prover and one very short for the verifier. And then, using this common reference string, prover can choose any NP statement such that there is a W that program on A and W outputs Z and produce a short proof for it. And then later, verifier can take this short proof and check its correctness. And moreover, the proof is zero knowledge, meaning that it leaks nothing about the statement except its correctness. In particular, nothing about the witness. So SNARKs are a more efficient version of another primitive called NISX. So let me compare the two explicitly. The highlighted differences are as follows. For non-interactive zero-knowledge proofs, common reference string is small, but proofs are long, and verification is expensive. So for concreteness, let me fix an NP-complete language of circuit satisfiability. And SNARKs are succinct. The proof is just of constant size, and verifier runs proportional to the input, not the circuit size. And this succinctness means that you can run long computations on an untrusted platform, like cloud or hardware with Trojans in it, and still yet easily verify the results. However, SNARKs come with a caveat, and that is this: that known constructions seem to require stronger assumptions. But that said, succinctness is really a wonderful property that might provide significant savings in practice. So in this work, we strive for this. And our goal today is to achieve SNARKs for arbitrary programs in practice. And in this paper, we achieve the goal. We build SNARKs for high-level programming language C, and our SNARKs are efficient. Concretely, if you take a C program that takes T cycles to execute, then CRS generator and prover are both quasi-linear in T. The verifier runs in time that's linear in the input size, and in practice, that is just milliseconds. The proof is constant sized, it's just 322 bytes for us, so it well fits in a single TCP packet. So before going into details, I want to give you a high-level overview of the main components of our system. What we want is SNARKs for C programs, but the best-known SNARKs in theory are all for languages like CircuitSat. So the first thing we do is we build a new SNARK for circuit satisfiability. And then we need to bridge the gap between C programs and circuits. And we do it in two steps. First, we design a new architecture called TinyRAM that's specifically optimized for verification. And then we build a GCC backend for it. Next, we build a circuit generator that produces small circuits that check correct executions of TinyRAM programs. And then we feed those circuits to our SNARK. Each of our components is highly reusable. For example, if you didn't want to use SNARKs, you can use circuit generator or circuit generator for just the standard NISX. So I will go top down and will first tell you about TinyRAM and our compiler. So starting from C's program, the most natural thing you could do is to compile it for some random access machine. But which random access machine should we choose? We essentially have very many options. But for the purposes of verification, we have two criteria. And they are as follows. First, like anybody else, we want the assembly code to be short and efficient. And second, as we are going to write a circuit that checks correct execution of this program, we want the instruction set to be as simple as possible. So let us look at how existing CISC and RISC architectures perform against this criteria. Both of them have quite efficient code, but instruction sets are quite complex. And this holds even for embedded architectures. For example, ARM has 35 SIMD instructions for addition and subtraction alone. So what we would really like to have is have significantly simpler instruction set, and we might be willing to pay for it in terms of less efficient assembly code. So in this work, we built a new random access machine model called TinyRAM, which I'm going to talk to you about next. So TinyRAM is our new architecture that is specifically tailored for fast verification. The instruction set of TinyRAM is so simple that it fits in a single slide, and its specification is available online right now. And TinyRAM has all the essential instructions for a useful architecture. For example, it has logical and arithmetic instructions, signed and unsigned comparisons and branches. It has instructions to read and write from random access memory. And it also supports reading non-deterministic advice for NP computations. So it seems like it fulfills our second criteria. It's really simple. But what about efficiency? Our experiment shows that TinyRAM is competitive with leading CISC architectures such as x86. So what we did was we compiled typical programs for x86 and TinyRAM, and we found out that code size and execution time are usually within a constant factor, typically 3 or 4, away from x86. And we have more illustrative examples and graphs in our paper. However, looking ahead, one step of TinyRAM CPU can be verified in just 1,000 gates. So to see how this is done, I would like to discuss the second component of our system, the circuit generator. The goal here is to take a TinyRAM program and produce a short circuit, a small circuit, that verifies its correct execution. So to first do that, let me introduce an object called execution trace. An execution trace of a program is just a time-sorted list of CPU states. So here it is. It contains timestamp, program counter, and the registers. And our goal is to design a circuit that checks if this trace is valid, meaning that it is code consistent, that instructions are executing according to the CPU specification, and that it is memory consistent, that from perspective of CPU, what you store in memory, which is not part of the trace, is what you get when you later load from it. So I would like to start by explaining code consistency, as from a conceptual perspective, it is a bit easier. So what we will do is to take execution trace, shown here, and apply the CPU's transition function to each 2 consecutive states. And transition function is a circuit that takes 2 states and check if the one can logically follow from the other up to the memory consistency. And so if we apply transition function to each 2 consecutive states, we would be ensuring code consistency of our TinyRAM trace. And inside this transition function, you would have things like in every normal CPU, like register file multiplexing, or checkers for ALU, and other things. So this would take care of code consistency. But what about memory? And memory consistency seems to be much harder. That intuitively, the problem is this, that memory is external to the CPU. And what gets written now might be read at completely unpredictable time later. So one way around this problem is would be just to maintain a memory snapshot with contents of memory for each time step. So here we would take the execution trace, and we would add the memory snapshots for each trace line. This naive approach obviously solves the memory problem, We have all addresses on the single slide, so it's easy to verify. However, it is also easy to see that this tableau is of quadratic size. So to verify it, we would get quadratic sized circuits in the worst case. So maybe we should look for a different approach. One different approach would be just declaring that memory addresses must be known constant, must be known at compile time, at a priori known constants. But we don't believe that this is sufficient in practice, that it limits our functionality. Memory addresses do depend on data, and this pushes the problem upstream, where the programmer must think about how to deal with them. So we need a completely different idea to solve the memory consistency problem. And what we do is we take observation from recent theoretical work that if our trace is sorted by memory address, then it is easy to verify. So here we have such a trace. It's first sorted by memory address and then by time. So all the accesses to address 0 are grouped together. So are all the accesses to address 1, and so on. And now that addresses are grouped together, it's easy to verify that to what you store is what you get, because the trace line is just the next trace line, or that memory doesn't change between two reads from it. And I just described two cases of what we must check in our memory consistency circuit, but there are two more cases, and they are all fit on one slide. And the point is that circuit for checking memory consistency is really simple. So our final circuit would look something like this. Its input would be the time-sorted trace of our executed program, to which we apply transition functions, circuits that check code consistency. Then the prover would provide an auxiliary advice, non-deterministically chosen. And this auxiliary advice is execution trace sorted by the memory address. And then we apply memory checking circuits to it. And to check if this auxiliary trace was really correctly sorted, we use a routing network. And for that, we actually inject more non-determinism for switches of the routing network and their positions. And the final expression we get is this. And while those asymptotics look quite manageable, the question is, what about concrete efficiency? What happens when we get down to the practice? And in this paper, we work very hard to obtain an asymptotic expression above with constants that are wonderful, that are really manageable for practical applications. And to do that, we leverage two techniques all over our work. First, we introduce additional non-determinism. To give you a very simple example, instead of computing division, you could just non-deterministically guess the division result and then check by multiplying. And second, instead of using Boolean arithmetic, we note that our underlying SNARK actually supports arithmetic, not Boolean circuits. So we can use native field arithmetic instead. And both of those techniques are not used just in ALUs, they're used all over the place and very crucial to obtain good circuit sizes. And the circuit size we obtain for a typical setting is this. And as you can see, the constants, including the one for quasi-linear term, are quite small. And the punchline is that if your computation takes no more than a million steps to execute, then it takes no more than 1,000 gates per cycle to verify it. So finally, let me tell you about the last component, our SNARK for circuit. Unfortunately, there is not much time left, but viewed from a space, a good SNARK construction consists of two components. Number one, you need something called linear interactive proof, which I'm not going to explain today, and you need a good elliptic curve encoding for it. And in this paper, we also worked to customize both to our setting at hand. So we designed a new linear interactive proof based on quadratic arithmetic programs. And we also designed good coding based on Tate pairings on customized Edwards curves. And I would invite you to look in our paper for more details. So, snap, snap, snap. To best of our knowledge, we are the first teams that achieve SNARKs for arbitrary programs. But there's lots of prior work that achieves implementations of various special cases or relaxations. And I'm going to describe it right now. In situations where those special cases apply, you may be better off in terms of efficiency by using them. For example, most work mentioned here is an interactive setting, while in our setting we produce non-interactive proofs. There has been work on low-depth circuits, and we work with Aleph and P. There has been work for verifying batched MP computations, where the savings come when you have multiple proofs that are verified together, while we get succinct verification either for a single theorem. And there has been a work on something called succinct refereed games for polytime computations, where you assume that you have many provers of which at least one is honest. And in our setting, we assume that the prover is adversarial. And more recently, at the beginning of the summer, there was an independent work at Outland Conference which strived for similar goals. And their system is called Pinocchio. And there are differences between our works, but probably the most important one is in our circuit generator, that they assume that memory addresses are known constants that are a priori known as the compile time, versus we support arbitrary programs. So let me show an example of how this is used. So let us fix a graph and consider the following language. The pair vertex comma distance belongs to the language if there is a Hamiltonian path starting from that vertex which doesn't exceed the corresponding time bound. And equipped with this graph, which you might recognize as UCSB lecture halls, or approximately, we can write a very simple decider for this language. And the following C program will verify if the path is valid for a given traveling salesman instance. And the program will look like this. First, it will read the input, the source vertex, and the maximum distance. Then it will check if the path doesn't have a cycle or exceeds the length. And finally, our metric is going to be L1 norm in 2 dimensions. So what I run before coming to the talk on my EC2 cloud instance was the following script. It first got the proving key or the prover's part of the CRS from trusted server somewhere else. Then it asked me for the starting vertex and maximum distance. And then the prover worked very hard to actually solve the TSP instance. And then it worked even harder to prove to me that my decider accepted this purported solution. And finally, it emailed me the proof as a QR code. So let us look how the proof looks like. And try to verify it. So, second. Oh, snap. What? OK. Those things are really hard. OK, good. So I have a proof right here. And it was emailed to my Gmail account, which I can show you. And it was this. So let me take my smartphone, which is obviously a computationally limited device, and check the proof. So the statement that the prover sent to me was this. That it knows a Hamiltonian path from Manzanita village of the specified length. So what I'm doing right now is taking the verification key from the trusted generator. And what I'll be doing next is scanning the proof and verifying it. So snap. So it really worked multiple times before, so it should be an indication that I shouldn't give crypto demos. But no, it read it, and it approved. So you can see green here. Really green, approved. Thank you. And I would like to finish by stating the same theorem that I mentioned in the beginning of our talk, that the correct execution of arbitrary C programs can be verified in a few milliseconds and 322 bytes. And here's the QR code for the proof of this statement. And our SNARK app is not able to verify it, but you can by going to our website. I would like to take this moment and thank our wonderful programming team and gracious sponsors, and finish by asking the following question. What would you like to prove today? We are looking for interesting applications for succinct verification. So if you have any cool ideas in mind where this could be useful, then please come talk to us after the talk. Thank you.